Yes. Good evening. So myself Arish, and we are here for the 8th live interaction session for Algebra second course. So we have already seen the first three questions of assignment 5. So we will start with the fourth question of assignment 5. Assignment 5 solutions we are discussing. So uh, yeah. So here is question number 4. So it says let M be the field adjoining iota with root with q. M dash is the field adjoining omega with q, and M dash is the field adjoining iota and omega both with uh, q. That is M double dash. So where omega is just a primitive third root of unity and iota is the primitive second root of unity. So we have to choose the correct options. So first one says that automorphism group of M over Q is isomorphic to Z2. So that means this group is the set of all automorphisms of M fixing Q. Okay. So this group is isomorphic to Z2. That's what the first question says. So yes. So solution is, so there are two ways to look at this problem. So first is you try to find explicit automorphisms. So that's what we are going to discuss first. Method 1. So what is this odd M by Q? So let's say this is for, so this is the set of, maybe I will just write it K over Q in general, K over F maybe. So this is the set of all automorphisms of K such that sigma of A is equal to A for all A belongs to F. And K is definitely an extension of F. So all automorphisms of the field K, which will fix the base field F, that we will say uh, that will come under this set ought K over F. Clear? So now for the first part, M is Q adjoined with I, right? And this is nothing but the set A plus BI such that A and B belongs to Q. Now, if some automorphism say F belongs to what M over F or M over Q here, then what it will do? It will do F of A plus B iota, that is F of A plus F of B, F of iota, right? And this will be just A plus B F of iota, right? And since iota satisfies x square plus 1, F of iota should also satisfy x square plus 1, and This implies f of iota can have only two choices, that is plus or minus iota, right? So this implies the cardinality of odd m over q is, or maybe not just cardinality, we have actually explicitly defined what are m over 2. This contains two maps, f from uh, m to m, f1 from m to m, such that f1 of iota odd is equal to iota, and f1 of alpha is equal to alpha for all alpha belongs to q. First is this, and it has f2 m from m such that f1 of iota is iota, and f1 of alpha is equal to alpha, sorry, minus of iota for all alpha belongs to q. These are the just two possibilities for uh, any element of m modulo q. So this implies the cardinality is 2, and definitely any group of order 2 is isomorphic to Z2, and that is also evident from here. This is the generator. If you square it, you will get F1, right? So out of M by Q is nothing but uh, is isomorphic to Z2, right? Now, this is first way of doing it. Second way is without even computing the uh, group. Also, you can see. So first observe that M upon M by is a Galois extension. Can you say why it's a Galois extension? Why it is normal and why it is separable? So finite is also there. It's a finite Galois extension. So finite is clear. It is a Galois. Normal is there because since M is the split splitting field of x square plus 1 over q, right? This is the smallest field containing the this root, and why it is separable? Since characteristic of q is equal to 0, and for q characteristic 0, any algebraic extension is a Galois extension. Sorry, any algebraic extension is separable, and m over q is an algebraic extension, right? So it's a Galois extension, and in lecture notes we have seen the following result. So it's the finite extension following theorem. This is very badly written. Okay. So which theorem I'm saying? So let K be let K over F be a finite extension then K over F is a Galois extension if and only if the dimension of K over F is same as the automorphism order of the automorphism group of K over F. So uh, thus in our case we already have the extension to be Galois and it's finite also. So this thing should hold. Thus in our case what we will get the dimension of M over Q is same as the order of automorphism group of K over F. And what is the order of what is the dimension of M? M is Qi, so it has dimension 2, right? So this implies this is of dimension 2, and any group of order 2 is isomorphic to Z2, right? Here I should have written M over Q. So this is the second way of doing it. Whatever way you like, you can solve this question. Okay, so you're saying 2, fine. So similarly, we can handle other parts as well. The second part is M dash over Q is isomorphic to Z3. So M dash is Q over omega. So let me just give them some number A, B, C, D. So let's say this is A, this is B, this is C, and this is D. It's M dash over Q. We should look at. So yeah, this is B part of M dash over Q, right? So now can you say what is this group? So here M dash is Q omega, right? And this is an extension of Q. So now M dash is the splitting field of splitting field of saying something degree 2. Good. This is the splitting field of x cube minus 1 over q, right? This implies M dash over q is a normal extension. Also characteristic of q is 0 and M dash over q is an algebraic extension. This implies m dash over q is a separable extension. And combining both the things, you can say that m dash over q is a Galois extension. Thus, same theorem we can use, hence by the same theorem, so it's a finite Galois extension also, right? We have the dimension of m over q is same as the order of the automorphism group, right? And what is the dimension of uh, m dash? M dash is q omega. It satisfies that is again 2, right? Since omega satisfies, omega does not belongs to q, and omega satisfies 1 plus x square over q, right? So yes, thus we get again that the automorphism group is isomorphic to Z2, not Z3, right? So option B is not correct because it says it isomorphic to uh, Z3. Now what about M dash, M double dash over Q, right? So let's see. So here, one thing is clear that both in both the options, it's saying that the order of what M dash over Q is 4. So the second method won't help because it just gives you order. So from there, if you can get that its order is not equal to 4, then you can definitely discard both the options and just say that the first option is correct. But if you get that its order is 4, then you can't say anything else because it doesn't say what kind of elements will be there. So we will use the first method with that try to explicitly say what automorphisms are, and through that we will see if the options C and D are correct. Because if you apply that the second method, you will get that the order is actually 4. Okay. So yeah. So C and D, we will handle both of them combinedly. This for that m dash is q over I at omega. So yes. So observe that m dash is nothing but a plus iota b plus omega c plus iota times omega d. That's it. Because iota square is -1, and omega square are dependent because you have 1 plus omega square to be uh, 0. So this is the linearly independent set you will get. So this is A, B, C. T such that A, B, C, D are inside Q. Now, what uh, you can say about the automorphisms? So, first thing is clear. Any F belongs to M dash, uh, sorry, odd of M dash on by Q is completely determined So what are the things, elements on which you should look the image? So this is completely determined by f of iota and f of omega, right? Because it fixes q, and if you know f of iota, f of omega, you will know f of iota times f of omega also. So that's not a problem. So yeah, and f of iota must satisfy x square plus 1 of iota with f of iota satisfying. Okay, we will write a separate line for that. Let this be done here. Okay. Now, also f of iota must satisfy x square plus 1, and f of omega must satisfy 1 plus x square over q, right? Because iota satisfied x square plus 1 and omega satisfied x plus x square plus 1. And yes, so this implies f of iota can be either iota or minus iota because it has root that, and f of omega can be omega or omega square. The roots of this polynomial is omega and omega square. So how many possibilities you have? I should write it as iota or minus iota. Thus, there are four possibilities. Am I saying something? Four. Yes. So what are those? Let us just list out quickly. So first is identity, right? You fix both. Second is means, in second, third, and fourth, you have to change at least one. So first one is f is identity. Second one is f is from m to m such that f of iota is iota and f of omega is omega square. Third is f is again from m to m such that f of iota is minus iota and f of omega is omega. Fourth one is f is from m to m such that f of iota is minus iota and f of omega is omega square. So let's say this is f1, this is f2, this is F3, and this is F4, right? So automorphism group of M O double dash over Q. I'm using M. I should not use M. The notation is M double dash. Okay. So yeah. So it has four elements, and they are identity map, F2, F3, and F4. So observe that F2 square is identity, because we are sending identity to identity again. It's a square will send identity to identity. Omega is sending omega is being mapped to omega square. Then again, if you apply, then it will map omega square to its square. And what is the omega square square? That is omega 4. And since omega cube is identity, so this is nothing but omega. So omega is mapping to omega in square, right? So, and q is anyway fixed. So F2 square is identity. What is F3 square? I is mapping to minus I. Then F3 square will map minus I to uh, F3 square will map I to minus I, and then minus I will be mapped again to I. So it's fixing again I, and omega is anyway fixed. So F3 square is also identity, and F4 square is also identity, that you can see. So all these elements have order 2, means it's just, it's not Z4, this is Z2 cross Z2, right? Because if it is Z4, then there should be an element of order 4 which is not there. There is one identity element and 3 elements of order 2. So it's Z2 cross Z2, right? So the third option is correct and the fourth one is wrong. So yes. Any doubt in that? If not, we will move to the next question. You are saying something? No, sir. Okay, good. So this, yeah, 2 has come. Just a second. So this is question number 5. It says let F5 be the field of order 5. We have to choose the correct options. Yeah. So first two are kind of straightforward. There is uh, nothing to be done. I don't know why they have given it. So, but yeah. So see, F56 is simply an extension of F5, right? And what is the cardinality of f(5, 6), that is 5 raised to 6, and which is order of f5 raised to 6, and that simply implies that the dimension of f(5, 6) over f5 is 6, not equal to 5. So this one is wrong, this one is correct. Second part, we have to see that it's uh, cyclic or not. So for part second, so is there any okay, so it is a cyclic group or not, that we want to see. So from video lectures, so first of all, it is easy to see that it's a Galois extension, although that is not needed, but still you can have that with you. Is a Galois extension, and what is why it's a Galois extension? So this is because any field Pn contains all the roots of the polynomial x raised to Pn minus x. So f(5, 6) is the splitting field of the splitting field of x raised to P6 minus x. Oh, sorry, P is 5 here, so I should write 5 raised to 6. X raised to 5 raised to 6 minus x over f5, and so this is a splitting field, so normal is there, and this polynomial is separable because all of its roots are distinct, right? And for a finite, even for a finite field, you have an interesting result that any field, finite field of is separable. Finite extension of a finite field is separable. That's because we read we had this result that if characteristic of f is p, then any algebraic extension is separable if and only if the field is perfect, and the field is perfect if the field is a finite field. So any finite extension of a of fp is separable, right? So this is because any finite extension of a finite field is separable. So that something was there in the lecture notes. So this is separable as well, and normal is already there, so it's a Galois extension. But we actually don't need that. Just I want to emphasize on the fact that this is a Galois extension just for a revision kind of thing. So although this is not needed, so this is just a bonus thing. Okay, so the solution is Let phi is the pair from F56 to F56, the Frobenius map. I hope you remember the definition of Frobenius map. This is a map sending A to A raised to 5, sending in general, sending A to A raised to P for all A belongs to F56. So uh, then from like video lectures, out of F56 over F5 is nothing but the group generated by this phi 1, phi square, phi cube, and so on, phi 4, and then phi 5, right? So phi a will give you a raised to 5, square will give you a raised to 10, right? And then a 15, 20, and 25, and then phi 6 is again identity. This is the group generated by the phi, and this implies that out of F56 over F5 is cyclic. Okay, so the third option is correct, while the fourth one is not correct. Okay, yeah, I hope that is clear, and we can move to the next question. You're saying something. Last step. Okay, so in the last step, what I have done. So in the so this phi for any finite extension FPN uh, of FP, you can define a Frobenius map from FPN to FPN, sending the elements to its pth powers. So in the video lectures, it has been shown that the automorphism group of FPN over FP is generated by this phi. So the automorphism group is this, thus it's a cyclic group. Whatever I did earlier was not needed. That is just for your information that it's a Galois extension. Okay, but the solution is just this. So it's a cyclic group. There were two options, cyclic or non-abelian. So cyclic option one is correct. Okay. Now you have typed something. Okay, sir. Okay. So let's move to the next question, which says that let Q be the uh, extension of Q adjoining third root of 5 uh, and omega, and then L is the extension that that is adjoining Q with the third root of 5, and F is just Q. So you have mm, so there are two groups. First is the automorphism group of K over F, and the second automorphism group of K over L. Then we have to choose all the correct options, right? So there was a theorem that can be directly applied here. So first of all, what's the situation? So you have F, that is Q, you have L, that is Q adjoint with cube root of 5, and that is K is cube root of 5 and omega, both are adjoint. So in lecture notes we have seen the following theorem. The theorem was saying degree 6. Degree is 6, fine, but we are not concerned about the degree. We are here concerned about the normality of the group. So degree is fine. So theorem says let K over F be a finite Galois extension, and let E and H corresponds correspond under Galois correspondence. So what is Galois correspondence? That is the fixed field of K with respect to H is E, and the automorphism group of K over E is H. So H is some subgroup of automorphism of K over F, and E is the subfield between K and H. Okay. Then E over F is a Galois extension if and only if H is normal in G. Right? So the correspondence is like that. You have K, you have E, you have F, and you have automorphism group of K over F. Then and it's you have a subgroup of it, that is H. So H is corresponding to K in the sense that the fixed field of K with respect to H is E, and the automorphism group of K over E is H. So this is the Galois correspondence. In while defining the final, while discussing the fundamental theorem of Galois theory, we have seen this correspondence. So how we can use this in our case? In our case, we have K, L, and F, right? So here we have K, L, K, E, and F. So let me just draw this again. I should not have erased it. So K, E, and F. Now it says E corresponds to H. So here L will corresponds to the group out of K over subgroup out of K over L. So in our case, L corresponds to H, right? That is a group out K over L. In the theorem, it is odd k over E. Here, it is odd k over L. So this is the H. So H is a normal subgroup. And L corresponds to H. So H is a normal subgroup of G if and only if L over F is a Galois extension. But is L over F is a Galois extension? No, because L is Q uh, adjoined with 3 root of 5 and F is Q. But L equal to Q cube root of 5 over F, that is Q, is not a Galois extension. This is because cube root of 5 belongs to Q, oh, belongs to L, satisfies so this has minimal polynomial x cube minus 5 over Q. This is minimal because it satisfies it, and this is irreducible using isolation criteria. So this is the minimal one. So over Q, and the splitting field of x cube minus 5 over Q is K. That is Q containing cube root of 5 and omega is K, not L. Thus, L over F is not a normal extension. So if it is not a normal extension, it cannot be Galois, right? Because Galois means normal plus separable. This implies H is not normal in G, right? So first one is wrong, second one is correct. It's a subgroup, of course, but it's not normal. Yeah. Now can you say something about the third one and the fourth one? These are easy, right? You can simply take G is cube root of 5 belongs to L. You can simply take Z to be identity over L. Right? Identity map is an automorphism, and it will map 3 cube root of 5, cube root of 3, sorry, yeah, cube root of 5 to cube root of 5, which is inside L. So that will work. So there exists an element such that the G, so here it should be G prime. There exists an element G prime belongs to G such that G prime is not inside L. That is also correct. So one can take G prime from, so it's a map from K to K, right? So inside G means it's an automorphism of from K to K such that G prime of cube root of 5 is cube root of 5 times omega, which is not inside L. So this should satisfy the polynomial that is satisfying by cube root of 5. So cube root of 5 satisfying x cube minus 5, right? X cube minus 5, and it has roots cube root of 5, cube root of 5 times omega, and cube root of 5 times omega square, right? So you can map it to any root. So here I am just mapping it to omega, and omega is not inside L. So that will do the job, right? So we have mapped it outside L, and why we are able to do so? Because it's not the it is not the splitting field. If it is the splitting field, if it would have been the splitting field, then it would have contained all the roots. So whatever root you map it, it would be inside the field itself. So it's not splitting, not the splitting field, that not a normal extension. That's why we can map it to the root that is outside the field, and that will do our job. Okay. So I hope that's clear. And we can move to the next question. So yeah, it says consider the fields K, that is Q adjoined with fourth root of 2 and iota. L1 is this, L2 is this. So let me just draw the correct diagrams so that you can have a better picture of the fields. So we have the base field to be Q, then L1 is Q adjoint with the fourth root of 2, L2 is Q iota, and what is K? K is fourth root of 2 times iota, uh, fourth root of 2 and iota. So yeah, so then we will use the same idea. It's saying that what are the normal subgroups of G. So yes, we will use the same theorem that is discussed in solution 6. Okay, that says that here also the correspondence is there, na? H1 is odd K over L1. So H1 corresponds to the extension K over L1, right? H1 here, H1 will correspond to L1 and H2 will correspond to L2 under the Galois sense, right? So we have to choose. So H2 is a normal subgroup. Since L2 over F is a normal extension, that's why the corresponding group subgroup, that is H2, is normal in G, right? The first option is correct. And for the second one, and since L1 over F is not a normal extension, because it's not the splitting field of the minimal polynomial of fourth root of 2, because fourth root of 2 satisfies x4 minus 2 over q, right? And this will have, that will have the that will have the splitting field k, not L1. So it's not a normal extension. So H1 is not normal in You're saying something. Doubt in option C. Okay, so option C we are coming. Yeah. What is H1 intersection H2? So H1 is the set of all automorphisms of K such that sigma of alpha equal to alpha for all alpha belongs to L1, right? So, but what is L1? L1 is being generated by Q and fourth root of 2. So this is nothing but sigma of A equal to A. This is very bad notation. For all A belongs to Q and sigma of fourth root of 2 is 2. Fourth root of 2 is root of 2. That is what L1 is. It's just generated by Q and fourth root of 2. So it is fixing L1 means it is fixing that. These elements, same. And H2 is similarly, okay, I will just copy paste this part and do the, oh, it can't be copy paste. I have to write it again. So this is sigma belongs to aught of K such that sigma of alpha equal to alpha for all alpha belongs to L2 and L2 is generated by Q and iota. So this is the field that will fix all Q and iota, right? So what is H1 intersection H2? H1 intersection H2 is nothing but the automorphism of K that is fixed in Q, right? That's what it is. So now, what is this group? This is nothing but your entire G, right? Because this is the definition of G, the set of all automorphisms which fixes Q. That's it, right? So H1 intersection H2 is G. So G is, or I am doing something silly here. Oh, no. It is intersection means it will fix 4 root of 2 and iota both. It is not union, it is intersection, right? So it will satisfy the condition of uh, both the subgroups. And sigma of I equal to I, sigma of fourth root of 2 is fourth root of 2. But your K is being generated by these elements only, right? Q and fourth root of 2 and iota. So it fixes everything. That means it contains just the identity over K. And identity subgroup is anyway normal in G. Okay. Now we hope that is okay. H1 is a subgroup of H2, clearly not. Right? that is easily being seen. So H2 is H1 is not normal. This is normal because it's just identity, and this is not. Okay, clearly. H2 is whether it's H1 subgroup of H1 subgroup of H2. H1 is not a subgroup of H2. You can see just by the definition of H1 and H2. You are saying something. Okay. So that's it. I hope we can move to the next question. Yeah. It says let G be the automorphism group of uh, Q adjoined with the eighth root of 2 and the eighth root of unity over Q. Then what is the cardinality of the group G? So check that it's a Galois extension. Is a finite Galois extension. Why it's a finite Galois extension? Finite is of course clear. Uh, Normal is there since it is the splitting field of x8 minus 2 over q. Separable is there because again the same thing that we have been using, characteristic of q is 0 and q cube root of 2 neta is an algebraic extension. ठीक है? Okay, you are saying 32. Good. So let's compute how it is 32. So by a theorem discussed in lecture notes, we have the order of q is root of 2 neta over q, same as the dimension of q eighth root of 2 neta over q, right? And what is the dimension of it? Dimension of the dimension, consider this tower of this tower. we have Q as an extension of Q root of 8, and which is an extension of Q, right? So this has degree 4 and this has degree 8. Since x square minus 8, sorry, sorry, x8 minus 2 is satisfied by 8th root of 2, and x8 minus 2 is irreducible over Q by Isestian criteria. Stein criteria. Okay, so this will give you degree 8, and why it has degree 4? Since neta satisfies x4 plus 1 over Q cube root of 8 2, and I leave it to you that x4 plus 1 is irreducible over Q 8th root of 2. Okay, so this implies that the degree of Q, and this is for Q, is equal to 32, and which will be the order of the automorphism group over Q. Okay, so that's why the order of the automorphism group is 32. So I think that's fine. We can move to the next question. So next question says, let G be the group, automorphism group of Q root 2 root 3 over Q. How many proper non-trivial subgroups does G have? So this I am not checking because I have been checking it for so many times that this extension is a Galois extension. It's very easy to see that it's a Galois extension. You can find the easily the split, the polynomials for which it's an splitting field, and I think we have already seen this the same example in the maybe in the last session or the session before that. So uh, observe that, or since this extension is a Galois extension, the number of proper subgroups of G is equal to the number of intermediate fields between q root 2 root 3 and q. So there are exactly three fields between this. We have exactly three intermediate fields that are precisely q root of 2, q root of 3, and q root of 6. Thus, there are three proper non-trivial subgroups of G. Right? So 3 is the correct option. Okay, so with that, I think we can move to the last question of this assignment. So this is just a theory-based question. So it says true or false. Let P be a prime and K be a finite extension of P, FP, that is K is just FPN. G is the automorphism of K, just the collection of all field automorphisms of K, and H is the automorphisms of K fixing FP. Then whether G is equal to H or not. So actually G is equal to H, and that's the solution is, so it's correct. This is not correct. So the solution is, so we know that FPN star is cyclic, and order of FPN star is also, we know, that is Pn minus 1, right? So let this be the group generated by some element, say A. So if some F is belonging to automorphism of K, then of course F of 0 is 0. That 0 is the identity, additive identity inside FPN, and F of any AI is of course F of A raised to I for all, for any, or maybe I can write it in more uh, simpler way, that, and for any alpha belongs to FPN star, there exists I belongs to N such that alpha is A raised to I, and Of course, f of alpha is nothing but f of a raised to I, because it's a automorphism, right? So what does this implies? This implies thus any f belongs to out of k is completely determined is completely determined by f of a. Okay, so it's just to see where a is mapped, because a is the generator of f of p n star. So it's just to see where this generator is mapped. Okay, and oh, also f of a will satisfy the minimal polynomial max of a over fp, right? That's because uh, a is satisfying that minimal polynomial. And since degree of or also we know that degree of minimal polynomial of x is n, right? Just a second. So yeah, so the degree of minimal polynomial is n, and we have already seen that any finite extension is separable, and fpn is separable over pn is separable because any finite extension of fp is separable, that we have already seen. So what are the possible roots that you can have? So for that, consider the Frobenius map. Sending a to a raised to p, then the uh, distinct roots of minimal polynomial of x are a, phi of a, phi square of a, and so on to phi n minus 1 of a. So these are the and distinct roots of a, and these roots will determine the value of f under the value of a under f, and that will determine the ought of k, right? So then f of a is some phi k of a dot 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 n, right? So this is how a is being determined, and in addition to that, the phi k of alpha is alpha for all alpha belongs to phi p, right? This implies your phi k is inside ought of k upon m f, and any uh, uh, f is also inside k over f, is also determined in terms of phi k. So you have the automorphism of k, that is p of n, is same as the automorphism group of k over f here in this case, right? So and both have cardinality n. That's what we are. Oh, there is no f here, so this is fp. You can write. They have not used the notation separately for fp, so just write fp here. Okay. So with that, the assignment number 5 is over. We still have some time, so we can quickly start assignment number 6, I guess. Okay. So I am not be revising the entire lecture notes in one go. What I will do, whatever we require uh, in between, that I will revise, and because unnecessarily revising the entire lecture will take a lot of time, and then we won't be able to like solve so many problems. Okay, let me just copy paste the first question. Hmm, just a second. I have to search the questions. Yeah, here it is. Here we have the first question. It says that Q adjoint with neta be the field extension of Q, when neta is the nth root of unity, then uh, choose all the correct options. So solution. So we can see this in all, I think all the options in one go. So what we require, that Q of neta In the from the lecture notes, we know that Q of neta over Q is a Galois extension. Why it's a Galois extension? Because it's clear that it's a splitting field of, because Q neta is the splitting field of xn minus 1 over Q, because all the roots of xn minus Q are what, right? So so this has roots 1 neta, neta square, neta cube, and so on to neta raised to n minus 1. So, and all these roots are present in Q of neta, and it's the smallest field containing all the roots. Thus, you have the second option is correct. That is, it's a splitting field of xn minus 1 over Q. So it's a splitting field, and characteristic of Q is 0. Characteristic of Q is 0, and Q neta over Q is a algebraic extension as well, right? These two things will give you the separable extension. So it's a Galois extension, right? So you have first one to be correct, second one to be correct, right? Yes. Now, from the lecture notes, ought of Q xi n over Q is nothing but it's isomorphic to un. That is the multiplicative group of uh, integers less than equal to n that are co-prime with n, right? So this implies ought of the group ought Q zeta n over Q has order same as un, that is phi of n, the Euler-Taussian function of n, and which means that first option is not correct, because phi n is not necessarily the same as n. In fact, it's never, I think it's never equal to n. So this is also not true because it's isomorphic to un, which is not same as zn. So second and third option are correct. Okay. So I hope that's clear, and we can move to the next question. Next question says, what is the eighth cyclotonic polynomial? So from lecture notes again, we know that xn minus 1 is product of phi dx. What's the notation they are using? Okay, phi dx such that d divides n. This implies x8 minus 1 would be the product pi d dividing 8 of the cyclotonic polynomial phi dx. So which is, what are the divisors of 8? 1, 2, 4 and 8 itself. So if we know phi 1, phi 2, phi 4, then we can just divide it, divide x8 minus 1 by it, and we will get phi 8, right? Also, in the lecture notes, we show that phi 1 x is x minus 1, and in fact, no need to like worry how it happens. So same thing you apply for n equal to 1. It says n minus 1 and then phi d of x divisors of n. What is the divisor of x? That is 1 itself. So n minus x minus 1 is just phi 1 of x. And phi 2 of x is x plus 1. How we get it? X square minus 1 is divisors of 2, that is 1 and 2. So phi 1x you have x minus 1. So you divide x square minus 1 by x minus 1, you will get phi 2 of x, right? So that is how you got phi 1x and phi 2x. Instead of show, I will say that we observed that. Oh. Okay. So this is now what is phi 2 of x? Phi 4 of x. Also, we have by the same idea here, x4 minus 1 to is same as the divisor of 4, phi 1 of cyclotonic polynomials of the divisors of 4, that is phi 1x, phi 2x and phi 4 of x. So this is x minus 1, x plus 1 and phi 4 of x, which implies phi 4 of x is x4 minus 1 divided by x square minus 1, that is x square plus 1. So what is phi 8 of x? Yes. Vivek, any idea? Now what is phi 8 of x? Hmm. So this implies from here x8 minus 1 is, what is phi 1 of x? This is x minus 1, x plus 1 from 1, x4, 4x is x square plus 1, and then you have 8 of x. So this is x4 minus 1. No, x square plus 1 and x, no. So this is 4x is x square plus 1. So this is 8 of x, which implies 8 of x is, you divide x8 minus 1 by x4 minus 1, you will get x4 plus 1. Okay, that is what 8 of x is. Okay, so that's what we are supposed to find. So I think we can move to the next question. Yes, x4 plus 1 only. Okay, so consider the uh, third question now. It says phi n x denote the nth cyclotomic polynomial. Choose all the correct options. Phi n x are monic polynomials for all n. So uh, solution first, and so this is directly by class notes. A is correct, B is not correct, C is correct by lecture notes. Simply, there we have seen that all phi n x are monic polynomials, and all phi n x are irreducible over qx, and it is in fact irreducible over zx. So now the fourth one, D part, we have to see. So it says phi p square x is phi p of xp. So what is, uh, we know that xp square minus 1 is product of all cyclotomic polynomials such that d is divisible by d divides p square. So what are the divisors of p square? It is simply phi 1 of x, phi p of x, and phi p square of x, right? Now give it 1, and for xp minus 1, if we apply the same thing, then this is phi 1 of x, phi p of x, right? So what is phi 1 of x? This is x minus 1, and this is phi p of x. So this will implies phi p of x is nothing but xp minus 1 divided by x minus 1, which is 1 plus x square, so on to xp minus 1, right? So from 1, we have xp square minus 1 is phi 1x and phi px. This is just xp minus 1, right? Clear, right? Because Phi 1x is x minus 1 and phi px is this polynomial. If you multiply them, you will get phi p, you will get xp minus 1. So this times you have phi p square x. So your phi p square x is nothing but x raised to p square minus 1 divided by xp minus 1. So you can see that this is nothing but a polynomial 1 plus xp plus x raised to 2p. You use the division of polynomial argument, divide xp square by xp, what you will get? Xp, right? And then so what I am saying, you divide this polynomial entirely by this, and then you will find that this is equal to, or maybe I should write it like that, x raised to p minus 1 p plus x raised to p minus 2 p dot 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 x raised to p 2p plus x raised to p plus 1. Or simply you multiply this polynomial by this, you will get that this is the what you will the outcome will come. Okay, so after dividing this polynomial by this, you will get this. So, and this is same as if you put replace x by xp here, right? So this is nothing but cyclotonic polynomial of p uh, replacing x by xp. That's what we are supposed to see. So D option is also correct, right? So D is, that's the third question. I hope that is clear, and then we can move to the fourth one. Oh, I have to change the page. Let me just. So it says let alpha is cos 2 pi by n. Then we have to choose what is the correct options. So we have seen the Gauss theorem, which says uh, we know that cos 2 pi by n is constructible is constructible if and only if n is 2 raised to a p1 p2 dot 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 um, pk where pi's are distinct Fermat primes. So what are Fermat primes? They are primes of the form 2 raised to m plus 1 for some m belongs to n. And also you have a greater than equal to a is belonging to natural number union 0 not just A, K can also belongs to this. It may be, it may happen that there is no prime in the product, mid prime, just a 2 power, then also it will help. It will do. Okay. So now can you quickly say that what are the numbers for which this condition is satisfied? It's an if and only if condition. Oh, forgot my charger. Maybe I will take it later. Yeah. So uh, yes, can you just quickly say what is or the values for which it happens? So maybe we can just see here tan is equal to 2 into 5 and 5 is 2 square plus 1. So this is a Fermat prime. So this condition, this is okay. Option D will not be the right option. Okay. So 12 is just 2 in 2. So this is 4 into 3 and 3 is also a Fermat prime. So this is also correct. 17 is a prime itself. 17 is 2 raised to 0 into 17 and 17 is 2 raised to 4 plus 1 and 19 is not correct because cross 19 and 19 is not of the form 2m plus 1, right? So yeah, then we can move quickly to the fifth question. Fifth question says that k equal to this uh, q o adjoint with the fourth root of -1 and f is q. We have to choose the correct options. Kf is a simple radical extension. So simple radical extension means it's some power of this is inside q. So this is correct since uh, if you take fourth power of it, then this is -1 which is inside q. So it's a correct option because some power is inside the base field. Q minus 2 is an intermediate field between K and F. So if it is an intermediate field, then -2 has to be inside, root of -2 has to be inside K. If it is not inside K, it will cross K, right? So it won't be. So we have to see. So this is option A, say this is B, this is C, and this is D. So solution of B, we want to see. So yes. So let alpha is uh, the fourth root of -1. Then of course you have alpha 4 to be minus of 1. So and alpha of 8 to be 1. This implies that alpha is nothing but the eighth root of primitive eighth root of 1, right? So this is e raised to 2 pi I by 8 and that is cos pi by 4, it's pi by 4 plus eta sine pi by 4 and which is 1 plus iota by root 2, because cos pi by 4 and sin pi by 4 are both 1 upon root 2. Okay. Now, yes, what is alpha square? This will implies alpha square is, you can check, this is just iota you will get. Shall I check it? Also, you have alpha to be 2 pi I 8. So alpha square is just zeta of 4, right? So alpha is zeta of 8, alpha square will be zeta of 4, that is iota. And alpha of cube is just multiply alpha by alpha square. So this is 1 plus iota by root 2 times iota. So this is minus 1 plus iota by root 2, right? And this will implies alpha plus alpha cube is 1 plus iota minus 1 plus iota by root 2. So this is 2 iota by root 2, and that is root 2 iota, and which is root 2 times root of minus 1, that is minus root of 2. So this implies minus root of 2 is alpha plus alpha cube, which is surely inside K because alpha is inside K. Thus, Q adjoint with minus root of 2, root of minus 2 is a subfield of K, and Q is, this implies that Q minus 2 is an intermediate field between K and F. F is 2, F is Q. This implies B is correct, right? So then we have to see what is the uh, whether out of K mod upon F is a cyclic group. So we know that K is just Q root of fourth root of minus 1, and fourth root of minus 1 is, we have already seen that it's zeta 8, and out of K over out of Q zeta n over Q is isomorphic to un. So this implies, so out of Q zeta 8 over Q is just U8, right? And what is U8? And U8 is isomorphic to Z2 cross Z2. It's not cyclic. So C is option is correct. C is wrong, and D is also wrong. Which implies C is not correct. Also, out of out of Q zeta A, maybe yes, we can work with zeta n itself, is same as the dimension of zeta n over Q, and which is uh, order of un, and that is, this implies Q zeta 8 over Q is same is the order of U8, which is 4. So D is also wrong because D option says it's 2, but it's actually 4. Okay. So maybe we can see one more question and then stop. Uh, Yeah, I think we can see one more question. So question number 6. So it says let K be the field adjoining Q, adjoining omega to Q. L is so let me just draw uh, the diagram for you. So in the base field you have Q, then you have L, which is Q cube root of 5. K you have Q omega, and KL is the smallest field containing KLL. So KL will be nothing but Q adjoined with cube root of 5 and omega. And I think we have seen the same structure earlier also in assignment number 5, if I am not wrong. Let me just go to the solution of assignment number 5. Somewhere I remember that we have seen this thing. It's iota and omega. This is same, right? Yeah. This is similar to question number 6. The same thing is there. But there the options are different. Here the options are slightly different. Okay. So here we are supposed to check the whether it's a Galois extension or what is the automorphism group. So KL over L, is it a Galois extension? So let me just give it some name: A, B, C, and D. So A, yes, KL is the splitting field of x cube minus 1 over L, right? Because just adjoining omega here, so it's just that, right? So normal extension is there, and characteristic of Q is equal to 0. Splitting field means it's an algebraic extension. So this implies KL upon L is a Galois extension. So the first option is clearly correct. And this also implies for the B part, since it's a finite Galois extension, is a finite Galois extension. Automorphism what can you say about the automorphism group? Automorphism group of order of automorphism group of KL over L is same as the dimension of KL over L And what is the dimension? So it satisfies x square 1 plus x square plus 1 plus x square over L. So this is just 2. And what is K, the automorph, what about L over F? So maybe I say that I will consider B and D together, because yes, it's good to see. So L over F is also a Galois extension. We have seen it number of times. It's just a splitting field of no, sorry. L over F is not a Galois extension. So it has two polynomials. So what are those? If F belongs to out of KL over L, then F fixes, then F of A is equal to A for all A belongs to Q. And since it is over L, so it fixes the cube root of 5 as well. And F of cube root of 5 is same as cube root of 5. Also, and F of omega should satisfies the polynomial in the minimal polynomial of omega. So it can be omega or omega square. So these are the two possibilities of it, right? But for L over F, you can have okay, for and if F belongs to automorphism of L over F, then of course, so since it is over F, so F of A is equal to A for all A belongs to Q, and F of this is what? This can be any root of the minimal polynomial, but the trick here is these two does not belongs to L. So these options cannot be there. So F of cube root of 5 can be only cube root of 5 itself. So this implies that F is just the identity over L. So automorphism group of KL over L is clearly not same as automorphism, or not just same at the level of isomorphism also. It's not true because it has cardinality just one, and the above group has cardinality 2. So they are not isomorphic. Clear? Now third part is out of KL upon L is out of KF. So this is yes. So K over F is, you can see, is a Galois extension. For K over F, in fact, we can directly compute if F belongs to out of K over F, then f of A is equal to A for all A belongs to Q, and f of omega can be omega or omega square, which implies the ought of K over F has cardinality 2, and the above group also has cardinality 2, and thus they are both isomorphic to Z2, KL upon L and K over F. So KL over L is isomorphic to K over F, and they are both isomorphic to Z2, right? And then the fourth one is of course not true. It's not a Galois extension. So D is not true since L upon F is not a normal extension. So yes, D part is not correct, and this is correct. This is not correct. Okay, so I think we will stop here, and we will see the remaining 4 questions and assignment number 7 in the next lecture. Any doubt? Wait, no. Okay, so I will stop here. We will meet on Friday, this Friday. Okay. Okay. So yes.